my comment, which is an organizational one, or a problem in terms of vision of the future of mathematics and physics, both, is that I looked into the question of how Greek science ended. And you have in the 2nd century a beginning of a decay in the number of people involved. That there were about 10 schools in the different places, 2 or 3 in Sicily, 1 in southern Italy, and Egypt. And you have a decay in the number of students, the number of people. It looks like the good minds are becoming interested in other problems, which are these issues of Christianity and perhaps some kind of social consciousness and things that came with monotheism and with these ideas at the time. And then there is also, of course, the church and at the end of the school in Alexandria, where Hypatia was the mathematician who was killed and raped by the crowd and so forth. I don't want to enter into the history, but the lesson for us, I see an effect of that nature in physics at least. We have now, we used to have the possibility of having the best students. Gradually, the students are going to study business administration and economics, perhaps, and things of that nature. And we are taking now students with much lower grade. And I don't know how it's in mathematics, but I think in general in the sciences, we have a lowering, the intellectuals are going elsewhere apparently, and they are attracted by these fields of which are connected with business and with economics. And the question is whether we have to be conscious of the thing and try and do something about it or not. The one hope there is that in computer science, the number is still large, or it sort of keeps up there. So maybe we can, through computer science, reintroduce the rest of mathematics and so on. I say it calls for thinking about the future of the disciplines, because of the fact that we've seen already science decaying once, almost completely.
Did you say numbers in plant biology?
Numbers in biology. I don't know what is the situation there. Yeah, in biology I don't know. But in the exact sciences, we see, in physics we have a very strong decay, and that's all over the Western world, everywhere. In Israel, we had for a while a renaissance when we had a million immigrants from the Soviet Union arriving, and they were not yet conscious or corrupted by the Western notions, and now it's getting that way again.
So during the talk by Arthur, there was one question which was sort of implicitly asked to Sergio right now. So might be the person who asked it should ask it again. Zakharov. Yes. I don't know.
What is known about classical field theory? Any particular young needs? Okay, so in classical field theory, just like in quantum field theory, there is a classification also, which is based on scaling. But it's done, instead of being done relative to the action, it's done relative to the energy. And for the Yang-Mills equations, the Yang-Mills equations are critical in 4 + 1 dimensions from the classical point of view. In 3 + 1 dimensions, they are subcritical, and one can prove regularity, global regularity for any data. So, and in fact, one can do even more. One can prove it relative to just the energy. I mean, just those data which are just H1. In other words, for which the energy is finite. And so the problem becomes hard in 4 + 1, which is critical, which nothing is known, and of course higher dimensions. But it's always 1 dimension less. So the critical case is 1 dimension less than in the quantum theory. 3 + 1 is okay, right?
Sorry? Oh, yes. Well, fine, sure, yes. Sure. Well, maybe I will check that the same job.
There is a great literature on 137. Well, the number became interesting in physics when, as I said, alpha, which was E square over 4 pi HC, yes, H bar C, when that number turned out to be very close to 1 over 137. And Eddington was trying hard to reproduce this from counting degrees of freedom and things of that nature. Two students, Hans Bethe and Riesner, wrote a letter to Nature in which they said, we think we have found the answer that Professor Eddington is looking after. Take a crystal at room temperature, freeze all degrees of freedom, so you freeze out 273 degrees of freedom, add 1 for the whole body, divide by 2 because of the spinning to the right and spinning to the left, and here you have the 137 coming out. Nature, the editor didn't check, and he published it. And Eddington became very angry and wrote an angry letter to Nature and so forth. So that's one. This is, if anybody is interested in the reference, I can find for you the reference to that. The second thing about 137, I heard from people, the person who was really there with Pauli. Pauli was ill, and who was it? This was a man who calculated the rearrangement of Dirac bilinears. Yes, he accompanied him to the hospital, and when they came to the hospital, it turned out that the room was room 137, and Pauli said, that means that I won't get out of this room, and he died there. The third story, and so that's a fact. The third story is that Pauli, when he didn't return from there, he went to heaven. And when he came to heavens, he was given the privilege to meeting with the Lord. And the Lord said, okay, if you want to ask any questions. And Pauli said, yes, why 137? And so the Lord went to the blackboard and started calculating, and Pauli kept doing like this. And finally, he showed him there was a mistake. My last 137 story, which is a true story, is that the president of the Israeli Academy at the time was Gershon Scholem, who was a great specialist on Kabbalah. And he was passing through Boston in Massachusetts, and invited to give a talk at the American Academy of Arts and Sciences. And Weisskopf was there. And Weisskopf was always interested in Kabbalistic things and things of that nature. And so Weisskopf asked Scholem, does 137 have any meaning in Kabbalah? And Scholem said, of course, Kabbalah is 137, and that's true. You know, the Hebrew letters have numerical values that you calculate in Kabbalah. That's some of the folklore on 137. Dana Mir seems to have another one.
I can add one just very simple thing. I heard from Zeldovich. Zeldovich told me that he had a bad memory and always forget a number where he put his coat in a garderobe in a lovely room, and to be sure that he never forget, he always used the number 137. He didn't put it on the
to have a cassette, a tape cassette, because a student of my son, piano, is also a student of a famous rabbi in Israel who does missionary work to convince people about Kabbalistic idea. So this one is named the holy number, or the important number 137 found in the Bible, and so on. So there are a lot of numerology tricks, like saying that 137 is the most frequent age in the Bible. 3 people in the Bible were said to live 137 years. This is Ishmael and Levi and Amram and so on. And this is the average of the age of Sarah and Jacob and so on and so on. So if anybody is interested, I can lend him the tape.
But are you sure that there are no other numbers with the same bracket?
Of course, you can do tricks of like that for almost any number, but anyhow, and then at the end of the cassette, you say, it says the scientists have only one explanation, one role for 137, but we have got so many of them.
There was this hoax with Wheeler where he claimed to compute it.
On a more serious topic, related. We were discussing 137 because of Eddington, and I was giving this as a false start in doing the Pythagorean kind of thing. And I did not give you examples of what we get really nowadays in particle physics because of the fact that that's why I said that we have materialized or realized Pythagoras' dream. For instance, we worked in from SU3 you add spin, and you have a system which for the static properties of particles you use SU6, and you calculate in SU6. It was at the time the first calculation done in SU6 was a calculation comparing the magnetic moment of the proton to the magnetic moment of the neutron using SU6, and the result was -3 to 2, terribly simple number, and they had never been divided one by the other. And when they were divided by the one by the other, of course, they are -3 halves. I mean, 1.5 is precisely, the precision is about 1%. Another result of that nature in SU6, the scattering on the same target, let's say the target can be a proton or a neutron, on the same target, you scatter a meson or a nucleon. And it's really, the group theory amounts to counting the quarks in them. And so the result comes out to be 2 to 3. And again, we've known for years there were these numbers. There were no reason existed. Why should the meson-nucleon cross-section be 26 millibarn, whereas the nucleon-nucleon cross-section was 39 millibarn? And that's precisely it. So we really have a realization of that dream of simple numbers, not numbers like 137. That's really too complicated.
This conference is about the end of the 20th century and the beginning of the 21st. I would like to compare it to the 19th century. In the 19th century, mathematicians knew physics and physicists knew mathematics. If you take the great names, no, not all. I mean, some not, but the great physicists knew mathematics very well, and most of the great mathematicians knew physics also very well, from the beginning, from Gauss to Poincaré, throughout, and so on. And moreover, they looked for principles, say the action principle, the constancy of the speed of light. This is actually a principle. No, this was a principle. I mean, what the greatness of Einstein was that he said that this is a principle. That this is a principle. It is not just a coincidence. This is a principle. No. I don't agree. He belongs to the 19th century. Also another feat of Einstein, that gravity is really the metric tensor. This is also a principle. It is a principle. When you No. Einstein was, well, it's not important. It's not so important. Well, maybe. Okay, so I can say, okay, so before 1920 and after 1920, okay? Okay, fine. Before 1920, because when quantum mechanics started, it was equations and mathematical models. No more principles. Just recall Jaffe's lecture today. Only equations. Lots of equations that actually we didn't see. We didn't see the equations, but you said there are equations, and we sort of yeah. But all of one after the other, equations and models, SU3, SU6, so on. All of it is models. So somehow I would be happier if no, okay, fine. Huh? Okay, maybe, fine. So tell us something. I mean, I say that it's a principle, so on and so forth. But somehow I miss this framework. And with this, I have a definite question that I asked Jaffe privately, and he suggested that I'll ask it publicly. Is there any physical theory that explains Coulomb's law? First of all, Coulomb's law is on the quantum scale, first of all. Yeah? It pertains to atoms. It is a combination of electromagnetism and mass. I mean, the gravity is small, but the inertial mass is not small at all. And as far as I know, maybe I don't know, there is no good explanation to this law. Of what? Does it? Together with inertia? I think it treats it on two different levels: electromagnetism and inertia. No? No? Okay. So.
You assume that, I mean, it comes in through special relativity.
So yes, okay. So the best known field theory, the one that I quoted in perturbation theory of quantum electrodynamics, the Dirac equation with the Maxwell field, in lowest order perturbation theory predicts the Coulomb force. But one very mysterious feature of this set of equations, which by the way we don't yet know whether there are mathematical solutions to the equations, is that physicists now believe, and I tend to think it's correct, that these equations have no solutions, that they have the same defect as the quartic wave equation in 4 dimensions that I mentioned, that they're inconsistent. And yet, the perturbation theory of these equations gives this most accurate number that we know in nature and calculate in perturbation theory. So you can ask whether that's a philosophical paradox. The answer in physics is that unless you make the equations more complicated and introduce the non-abelian gauge theory into the equations remain inconsistent. But is that the real way out? That is no. This is a number characteristic of electrodynamics. So, but it could be that this theory that we know best has no mathematical meaning. No, that it cannot have a meaning without being embedded into a larger theory.
Well, one of the stories about 137 is that just because 1 divided by 137 is such a small number, the cutoff at large energies that makes quantum electrodynamics well defined is at, say, 10 to the 137 electron volts. So if you're willing to introduce a cutoff at these very high energies, the theory is perfectly well defined and of course reproduces its perturbation theory. So in this sense there is no problem. Since I'm already here, should I ask? I thought it was very important that you mentioned first the openness of information and second the informational mess. Now of course physics has lived with an informational mess ever since the beginning of quantum theory, I would say. I think it was a little better in the last century because not much was happening. I mean, after Maxwell, in the last part of the 19th century, not much was happening. So we had this informational mess. Now, I think as long as there is a lot of progress and lots of new discoveries, we can live with it. Now, apparently, we are reaching a stagnating period, and so it becomes a little painful, and I think it's one of the reasons young people turn away from physics. I think what some of you great guys could contribute is to give people credit who just modestly do a problem which has already bears the name of, I don't know, Novikov or Gon or Schwinger or so. I think we tend to be a little greedy in not being willing to give credit to young people who just fill in a little piece in a puzzle. And I think we should do it because we cannot expect wonderful discoveries at the pace we saw them during the last 50 years. So this would be sort of a plea to be more generous with each other. Okay, maybe another observation. It seems to me this discussion shows that mathematicians like to be a little anecdotal. I think there are real issues to be discussed, and maybe we should really discuss them.
I think the one issue which was raised and which was not discussed, unfortunately, but there is very little time to do that, was many people asked, but there was no, I mean, you answered, but you didn't have time to really give a full-fledged answer, which is why is it required to have quantum gravity? I mean, I think, this was presented indeed as being the fundamental problem, but somehow, for instance, Sergei doesn't believe it's really needed. I mean, this is what you told me. I mean, okay, fine. But what I mean is that I can tell you just in a few words, I mean, what is the structure of the problem? I mean, the structure is, roughly speaking, the following, that, why do we have quantum fields and not just quantum mechanics? The reason is extremely simple. There is a small paper by V.Milman in the anniversary for Dirac's memorial in 1984. And the idea is the following. The idea is that when you look at quantum mechanics, there is a contradiction. And namely, there is a contradiction between causality on the one hand and positivity of the energy on the other hand. It's very, very simple to prove that. I mean, it's a few lines proof. And the only way out which is known is quantum field theory. Namely, the effect of quantum field theory is precisely, just by writing the quantum field, to reconcile causality with positivity of the energy. And this can be seen even from the point of view of classical field theory. I mean, you can very quickly understand that, for instance, if you take positivity of energy for the wave equation, you would have to take the square root of the Laplacian, but the positive square root. And this is a non-local operator. So that's a very fundamental fact, which implies that when you go to high enough energies, if you try to put particles in a very small box, there will automatically be creation of pairs. So this means that you cannot talk about particles and quantum mechanics in a coherent way. Now, on the other hand, we have gravity. I mean, there is no way out. We have gravity. And when you look at small perturbations on the vacuum, if you want, on the Minkowski flat space, what you find out is that the way to parameterize these small fluctuations is by waves. These waves are called gravitational waves. They have not been observed, But by binary pulsars observations, we know they are there. I mean, there is an implicit observation of them through the theory of binary pulsars. So now what happens is that you have these waves, you have this field, this gravitational field, and there is absolutely no way out from the point of view of physics that they have to be quantized. And the fact that the two theories are contradictory has been called, I think by Brian Greene, the biggest cover-up of the century. You see, I mean, there are two physical theories, and these two theories are in fact contradictory with each other. So of course this is a major problem. You can name it a theoretical problem, not a physical problem, because the quantities which are at stake, if you want, are so difficult to measure and so on, and they are only observable, say, in the Big Bang and so on. But for mathematicians, it's an ideal problem in the sense that, I mean, you know, it has this beauty of two theories which are perfectly well defined, but which are contradictory with each other. Sergio.
Just one small remark. I mean, it's clearly that Alain is right, and this is a problem that has to be solved. But one may also wonder whether the time is now. So, so one thing one can say is that, let's say, in 20th century, there was not just one revolution, there were two revolutions. One was quantum mechanics, and the other one was general relativity. And each one, if each one would have happened by itself, it would have taken maybe 100 years of development of mathematics to do it. Now, quantum mechanics, I think, has been addressed to a large extent, at least maybe not at the quantum, not for field theory, but certainly the non-relativistic case. Now, general relativity, however, at the classical level, has been completely ignored, as far as I can tell. I mean, with few exceptions. There's been very few. Well, you are talking about experimental level, but I'm talking at the mathematical level. The development at the well, this is perturbation theory and doing calculations, but I'm talking about the principles, the mathematical principles of general relativity, the way quantum mechanics was developed, and I think there was an enormous amount of interest from mathematicians, from the mathematical community to the classical quantum mechanics. This didn't quite happen with general relativity, and so I think that, you know, you may wonder whether we don't need, at least in parallel, to develop classical theory before really attacking the problem of maybe, I don't know, maybe a general quantum theory of gravity is a problem for I don't know, maybe not even the next century. Maybe it will take another. I mean, one thing about mathematicians is that we are very patient. Unlike physicists, I think we have the experience of problems that took hundreds of years to be solved.
Okay, thank you. So I think